Am I audible?
Yes, ma'am.
Okay. Mhm. Okay. So, very good morning, everyone. So, let us continue with this chapter, that is Haloalkane and Haloarene. Before that, in last lecture, we saw two type of reaction, that is SN2, SN1. Why it is known as nucleo bimolecular reaction? Why it is known as unimolecular reaction? Why? Because in SN2 it is known as bimolecular because the rate depends upon molar concentration of two reactant, that is CH3Br and OH minus. So uh, and the conformation is just taking place. It is a Walden inversion. It's very important. These questions they ask in NEET exam. In SN1, it is nucleophilic substitution unimolecular. One more thing I have to tell you. In SN2 mechanism, the reaction rate is it is primary, secondary, and tertiary. So why primary, secondary, and tertiary? What do you mean by primary, secondary? Primary means what? So if I'm taking bromoethane, okay. So we are only concerned about the carbon which is directly bonded to the bromine atom. So this is the carbon which is directly bonded to the bromine atom. So to this carbon, how many carbons are attached? Only one. So this becomes primary. Okay. If you want to, if I want to talk about secondary, so the carbon which is attached to bromine, if to that two carbons are attached, so that becomes secondary. This is secondary. And tertiary, it is CH3, CH3, CH3 and Br. So we are only concerned about the carbon which is bonded to bromine. So this is tertiary. It is very important. So the reactivity rate is first primary, secondary and tertiary. Why? Because in SN2 reaction, bond breaking and bond formation, you can see the bond breaking and bond formation between C and OH. It is everything is taking place simultaneously at only one step. So first primary is preferred, then secondary, and then for tertiary the rate will be very slow. Okay. And one more thing we have to keep one thing in mind is that in SN2 reaction, the solvent which is used over here is a polar, a protic solvent. And in that you have to keep example in mind, that is DMSO, dimethyl formamide, and acetonitrile. What do you mean by polar? Polar means when there is charge separation between two atoms. A protic solvent is nothing but a compound which is not having hydrogen atom. Like it is not bonded to oxygen. Like if hydrogen is not bonded to oxygen, that comes under a protic solvent. So you just have to keep these four thing in mind. That is, it is SN2. Why SN2? Because it is bimolecular. Why bimolecular? Because at rate determining step, there is presence of two reactant molecules. Then the conformation is Walden inversion. The reactivity is primary, secondary, and tertiary. And the solvent which is used over here is polar aprotic solvent. So for this, these are the four things which you have to keep in mind. Okay. Then comes SN1. So for SN1, the reactivity will be tertiary, secondary, and primary. Why? Here there is formation of carbocation. In this step, you can see there is formation of carbocation. And for carbocation, if you want to stabilize a carbocation, so what do you mean by carbocation? A carbocation is nothing but a carbon which is electron deficient in nature. So it is highly electron deficient. So they need electron in order to maintain their stability or in order to attain their stability. So you should have you should have groups which donate their electrons. So this is a tertiary carbon. Basically, this is tertiary. So when it is attaining the carbocation, you can see there are three methyl groups which are giving its electron to carbon atom and it is stabilizing the carbocation. So that's why the rate of the reaction is tertiary, secondary, and primary. In primary, if you see, there is only one carbon atom which is donating its electron. In secondary, there are two carbon atoms which are donating its electron. But in tertiary, there are three methyl groups which are donating the electron to maintain the stability of the carbocation. Done. And in SN1, we are getting a racemic mixture. So what do you mean by racemic? There is 50-50% formation of inversion as well as retention. What do you mean by retention? If you look into the starting product, if you look into the starting reactant, you can see Br is present on my right side. Okay, and in retention also the Br OH is present on the same side as that of the Br which is in the reactant. So that is retention. If it is present on the opposite side, then that becomes inversion. And a racemic mixture is nothing but there is 50% inversion and 50% retention. Okay, there is not like 50, 70 and 30%. Everything will be half and half. Then comes elimination reaction. We saw two types of elimination, which is Sedzep elimination or Hoffman elimination. Okay, so basically in Sedzep elimination, in nucleophilic also the reactant was OH minus, and in elimination also the reactant is OH minus. So what is the difference? In nucleophilic the reactant is aqueous OH minus, and in elimination the reactant, the attacking nucleophile, is alcoholic OH minus. So that time only we'll get a doubly bonded system. So here the OH minus is abstracting the beta hydrogen. The bond is breaking and it is forming between alpha and beta, and the Br is getting removed. Okay, so this is a general, but in this question we saw there are two beta hydrogen, so we are getting two possible products. But when you look into the product A, you can see it is but2ene. So you can say that is it is more substituted alkene. More substituted alkene is obtained as a major product. This is the rule which is given by scientist Sedzev. Okay, and in second B product, we are seeing that there is less substituted alkene. Then that is if less substituted alkene is obtained as major product, then that rule is given by Hoffman. Okay, actually this Hoffman is not in your syllabus, but to keep this in mind, just for your general knowledge, you have to keep these in mind. Okay, then we saw reaction with metals. So first word with Grignard reagent. Grignard reagent is nothing but it is RMgX, alkyl magnesium halide. And I told you if I want to make Grignard reagent, I'm going to take alkyl halide and in that I'm going to add magnesium metal. And even whenever you are using a magnesium metal, you have to use solvent as dry ether. Why? Because magnesium metal is reactive and it highly catches fire if it comes in contact with water. So a system should be dry. Dry in the sense it should be a system where moisture content is 0%. Okay. So what this magnesium will do? It will insert itself in between carbon and bromine, so we are getting methyl magnesium bromide, and this is nothing but Grignard reagent. If I'm treating this Grignard reagent with water, So water is H2O, so I made this counterparts as H plus and OH minus. In CH3 MgBr, CH3 is minus, MgBr is positive. So this negative part of the reagent will attach itself to the positive part of this water, and this negative part of water will get attached to the positive part of MgBr. So we are getting methane and MgOH. So your X is nothing but Br. This was the part which we saw, and we solved one example. Other is Wood's reaction, or we can call it as Wood's coupling reaction. So basically, Wood's coupling is nothing but we are going to couple two reactant molecule. But for coupling, we can't do it like that only. For that, we need a catalyst. And basically, for catalyst, we use a metal. So here, if we are using couple, if we are coupling it, right? So coupling means what? Between two, like we are joining two compound, two molecule to form a single large molecule. So if you are taking 2 moles of anything, you have to take 2 moles of that metal. Okay. So for the example, if you are taking 2 moles of bromomethane, so you have to take 2 moles of sodium. Again, we are using a metal, so we have to use dry conditions. So I'm using dry ether. Okay, so here we can say NaBr, and if you're taking bromomethane, so you're getting ethane. You just have to multiply it by 2. Okay, if you're taking chlorohexane, so what will be the product? Sorry, if you're taking, for example, chloropentane, so what would be the product? Pentane means 5 carbon. So you will get 10, right? 5 twos are 10. So you're getting decane. Decane. Okay. So that is Wood's coupling reaction. The other reaction over, sorry, okay, just a minute. I hope you're getting it right, Rahina. You're there?
Yes, ma'am.
Okay. We just revised the things which we did last time because there was a gap of 3 to 4 days. So, okay.
Okay.
So let us continue the next part. We saw Wood's reaction. The next part over here comes is second name reaction, that is Wood's fatigue. So when you look into this reaction, Wood's fatigue. So there are two sign like there are two parts, that is Woods and fatigue. So in this, again, this is a coupling reaction only. We are just going to join two molecule to form a one to form one molecule, right? So in this, there is Woods and one is fatigue. Okay. So Woods can be basically any alkyl halide. So let us take. Sorry. I'm taking CH3Br. And for fatigue, let us take. Fatigue means what? We are gonna take any benzene ring, alkyl benzene. Sorry, bromobenzene. Okay. Now again, I'm going to use 2 moles of sodium metal. What will happen? This Br and this Na will, again the reagent will be dry ether. So the byproduct which I'm gonna get is 2 moles of sodium bromide. What will happen? This CH3 and this benzene will join each other, will combine to form, what is the name of this product? Methyl benzene, and the common name is toluene. Okay. So for woods you have to take any alkyl halide. For fatigue you have to take a bromobenzene or any halobenzene or haloarene. And for that again you are going to take 2 moles of sodium. It is same as Wood's coupling reaction, but in Wood's fatigue. So there are two names in that. So you have to take two different types of alkyl halide. One you should take an aliphatic, and the second you should take aromatic. So that is Wurtz-Fittig reaction. Okay, fine. Next is uh next reaction is Fittig reaction. In Fittig reaction, Fittig is nothing but we are going to take benzene ring. Any bromobenzene you let us say. I'm taking bromobenzene. But again, this is a coupling reaction, so you have to take 2 moles of bromobenzene. And again, we are going to take 2 moles of sodium metal in the presence of dry ether. So what will happen? This Br and this Na will get removed in the form of 2 moles of sodium bromide plus this phenyl and this phenyl will attach to form a biphenyl ring. So in Fittig, we are getting a biphenyl system. Okay, this is biphenyl. This is a phenyl ring and this is a phenyl ring. So there are 2 phenyl rings. So we call it as biphenyl. Done? Okay. Yeah, you can. But if you're using Br, if you're using first, if you're taking bromobenzene, the next should be also bromobenzene only. You can't take chlorobenzene. Yeah, you can. Yes, but your system should be aromatic. Aromatic any benzene. So to that you can add any methyl group or whatever you want. Okay. If you, for example, if you're using CH3 over here, so what would be the product? So this bromine, what is the position for this methyl group? This is ortho, meta, and para. So in this benzene ring where you're going to situate, this is ortho, meta, and para. So you have to put CH3 over here. Done? This is my ortho position. So this is also my ortho position because where the Br is removed, there only the bond is formed, right? So it is like that. Sorry, this is met. This is para. Okay, fine. Now we are in the last part of this chapter, and this is very easy. That is electrophilic substitution reaction. It is very easy. Whenever you look into whenever you look into the chapters of organic chemistry, the last part, that is electrophilic substitution reaction, is common in each and every chapter. Okay, you just have to keep 3-4 reagents in mind, and what would be the electrophile from that reagent. That's it. You just have to keep these things in mind. Okay, so let us put on the heading, that is electrophilic electrophilic substitution reaction. Okay. Okay. Now, first lecture, last lecture, we saw the resonance effect. So basically, what we are gonna do? What do you mean by electrophiles? Electrophiles are nothing but they are electrophiles are electron deficient species. So basically, they have they have positive charge in it. It can be NO2 plus. Okay, so they have positive charge. In nucleophile, they have negative charge or they have lone pair of electron. Okay, so let us draw the resonating structure of chlorobenzene. Now this chlorine group has lone pair of electron, and this lone pair of electron will be busy in resonance with the benzene ring. So this bonding pair lone pair will come in this position. This bond will get broke and it will come at the ortho position and will get a resonating structure somewhat like this. Cl plus the bond has broken and it has come to the ortho position, so we are getting minus charge at the ortho position, and the remaining pi bond will be as it is. Okay, so this negative part will come at this position and this bond will break and it will come at the para position. So we are getting a pi bond over here, negative charge at the para position, and pi bond over here. The negative charge again, it will come at this position, this pi bond will break and it will come at the ortho position. This negative part will come and the Cl will get stabilized. Okay. So when you look into this A, B, C, D, and E structure, you can see in B, C, and D, the negative charge is there, right? In B, the negative charge is at ortho position. In C, the negative charge is at para position. And in D, the negative charge is again at ortho position. So, here the electrophiles are positively charged species, so obviously they will attack on the species that is negatively charged because opposite species attract each other, right? So the positive electrophile will attack on the negatively charged carbon atom. So the attack will take place at only ortho and para position. There is no any charge on the meta position, so there will be no any possible attack on the meta position. So we'll get a product at either ortho or either para. Okay. Now let us see the first electrophilic substitution reaction, that is halogenation reaction. So halogenation again. Halogenation is nothing but addition of halogen. Okay. So you take a chlorobenzene. You have to add. Now we are doing halogenation reaction. So you're adding chlorine. You're chlorinating it. Okay. So you're adding chlorine. So you just can't write Cl. You have to write Cl too because Cl, they chlorine or anything, they exist in diatomic state. Okay. Now, even if you put chlorobenzene and chlorine together, they won't react for any. They won't react. So for that, you need a reagent, that is anhydrous FeCl3. You have to keep these reagents in mind. FeCl3. Okay. So what do? You have to draw the reactant twice. So you are going to draw reactant twice. That is chlorobenzene. You have to draw it twice. We are adding chlorine, right? So what you'll do? You'll put one chlorine at ortho position and the other chlorine at para position. Done. Why chlorine? There are two chlorine, and in benzene there is hydrogen atom. So this hydrogen and this Cl will remove in the form of HCl, and the Cl will come and it will get substitute at this ortho. And the second possibility will get the position chlorine at the para position. Done. It's very easy. Okay. So what is the name of the first product A? 1,2-dichlorobenzene, and the second is 1,4-dichlorobenzene. So could you predict what would be the major and what would be the minor product? No. Major will be 1,4-dichloro. Why? Because chlorine and chlorine both are negatively charged species. So obviously they will try to minimize the repulsion between them. So this product will be my major and this product will be my minor. Done. If it is forming at 98%, this will form at 2%. Okay. So this is halogenation reaction. The next reaction is nitration. So in nitration reaction, again we are going to take chlorobenzene. So basically for nitration, the source is NO2. NO2 plus is my electrophile. So how this NO2 will form? So for this nitration, any acid which has nitration, which has nitro group in it? Concentrated nitric acid, right? So we are going to use concentrated HNO3, but it's not sufficient. So you have to use another acid with it, that is concentrated sulfuric acid. You have to use two reagents. Okay. So again, you're going to draw chlorobenzene two times. One you're going to add NO2 at the ortho position and the other NO2 will be at para position. So in this, with what would be the major part? What is the name of this What is the name of this product? Yes, yes, benzene. And this is 1-chloro-4-nitrobenzene. So the major will be this and the minor will be this. Why? Because Cl and nitro both are negative. So in order to minimize the repulsion, so the product is at the para position. Or we can even say in order to minimize the steric hindrance between them, because both are bulky groups. Okay, no, okay, fine. So this is nitration. Next in sulfonation, in sulfonation, the group which we are going to add is SO3H. SO3H. Okay. So what we are going to do is that we are going to take chlorobenzene. Now in sulfonation. So there is one acid which starts with sulfo. That is sulfuric acid. So in this, we're just going to add sulfuric acid. We are not going to add nitric acid, because if we add nitric acid as well, so it will undergo nitration. But we have to do sulfonation. So for this, you have to use concentrated sulfuric acid and you have to heat it. In nitration, you are going to carry out in freezing temperature at around 0 to 5 degrees Celsius, in between that. But for sulfonation, you have to heat it. So again, you are going to draw 2-chlorobenzene again. So you put one SO3H group at ortho and the other SO3H group at para. So the name of this is, so you have to number it from here. So this is 1 and this is 2. So this is 2-chlorobenzene sulfonic acid. This is 1, 2, 3, 4. So this is 4-chlorobenzene sulfonic acid. Again, this is my minor product and this is my major product, because okay. Okay, last two reactions are left. Let us see. One is Friedel-Crafts reaction, and in that Friedel-Crafts, we are going to learn about two types. One is Friedel-Crafts alkylation. The other one is Friedel-Crafts acylation. So let us look into Friedel-Crafts alkylation. In both, we have to use an aromatic halide. So I'm using chlorobenzene. And in alkylation, we are going to add alkyl group. So let us take any alkyl halide, chloromethane. So what will happen? We are going to get two products. Draw, you have to draw chlorobenzene twice. This is anhydrous AlCl3 aluminium trichloride. So what will happen? This H and this Cl will remove in the form of HCl, and this CH3 will come at ortho position and one will come at para position. So the name of this product is 1-chloro 2-methyl benzene. This is 1-chloro 4-methyl benzene. Again, this is major and this is minor. The para product will always be major and the ortho product will always be minor. So this is Friedel-Crafts alkylation. Next is Friedel-Crafts acylation. In acylation, we are going to add acyl group, that is CH3 C double bond OCl. So this is acyl group. Again, the reagent is anhydrous AlCl3. So what we are going to do, we are just going to add, in place of hydrogen, we are going to substitute this acyl group. So this we are, again we have to write chlorobenzene twice. One acyl group will be at ortho position and the other acyl group will be at the para position. So we are getting two products, that is 2-chloro. So this name is its name is 1 and 2. So this is 2-chloroacetophenone and this is 4-chloroacetophenone. That's it. So these are the products which we got, that is in Friedel-Crafts acylation as well as alkylation. So actually we are done with this topic of alkyl halide. This chapter is quite easy, This chapter, when you look into the organic chemistry portion, this chapter is very easy when you compare it with other chapters. This chapter, like you can score quite good because there is no that much name reactions and there is no that much things to just remember it. Okay, you just have to remember the reagents, the name reactions. So the name reactions in this reaction is we can just summarize it. So what are the name reactions which we have studied? First was Markovnikov rule. Second was anti-Markovnikov rule. Third was Swartz. Fourth was Finkelstein. Fifth was, I think, one sec. Yes, the Zef rule. Sixth was Hoffman. Seventh was Wood's reaction. Eighth was Wood's fatigue. Ninth was fatigue. 10th was Friedel-Crafts alkylation as well as acylation. So these are the 10 name reactions which we have studied in this chapter. So for Markovnikov rule, the system should be doubly bonded. The negative part will attach to the carbon having less number of hydrogen. Anti, again we need doubly bonded system and the negative part will attach to the carbon having more number of hydrogen. but the reagent should be peroxide. In Swartz, it is halogen exchange. So Swartz, which halogen exchanges from the alkyl halide? Which halogen gets which is the halogen in Swartz reaction? One that is fluorine. If I'm taking chlorobenzene, so if I add AgF, so I'll get fluoro. If I'm taking chloromethane, so I'll get fluoromethane. In Finkelstein, how can you remember it? In Finkelstein, the next letter after the F is I. So we are gonna replace it with iodine. In Sedzef, we are using it is an elimination reaction. So we are using alcoholic base KOH. So we are getting a doubly bonded system. In Hoffman, we are again using alcoholic base, but in Hoffman we are getting less substituted, and in Sedzef we are getting more substituted. Wood's reaction is nothing but it's a coupling reaction where we are coupling two aliphatic halogen derivative. If I'm taking chloromethane and bromo, if I'm taking chloromethane and chloropropane, what would be the product? Hmm? Chloromethane. In chloromethane, there is one carbon. And in chloropropane, it is three carbons. So 1 plus 3, 4. So we are getting butane. That's it. You don't have to multiply. If you're taking two same methane, if I'm taking two same chloromethane, so that becomes ethane. Okay. In Wood's phytic, Wood stands for aliphatic and phytic stands for benzene ring. And in phytic, both we are taking a benzene ring. Friedel-Crafts alkylation and acylation, we just saw it. We are getting two products. One is at ortho and the other one will be at para. There will be no substitution at the meta position. Okay. So these were the topics which we completed. Now let us see some basic questions, PYQs of these chapter. So in that, if we are solving that, then who's that? If we are solving it, then we'll come to know how much we have studied. Okay. Okay. Just I'll where is the questions which I sent them? Mm-hmm. Yeah, that's it. Okay. Okay, the question is, first question, I'll zoom it. Which of the following is least reactive in nucleophilic substitution reaction? You can see, right? Just try it. Am I audible?
Yes, ma'am.
Okay, okay. Hmm. Okay. That is a question. Or okay, we can solve it. This is take. Okay. Which of the following is least reactive in nucleophilic substitution reaction? So nucleophilic substitution, which means now a electron-rich species will attack on this particular reactant. So we have four reactant. Okay. So for electron, if nucleophile is attacking, so our system should be nucleophilic or electrophilic in nature. Nucleophile is attaching, so our system should be electrophilic because oppositely charge will attract each other. Okay. But in this question, the one thing is important is that they are talking about least reactive. The more reactive will be what? More reactive, which means if my system is more electrophilic, then that is more reactive. Okay. So we can say, can you guess any answer within this part? Okay. So let us draw. Second is CH3, CH2, Cl. Third is CH2 double bond,
Option
CH.
one.
Huh?
Option one.
Yes, option one. Could you just explain why it is option one?
Actually, to be honest, I guess rest all carbons are having more and more number of carbons,
Okay.
and
Yeah, I think whatever you guessed, it is right.
I guessed
Yeah.
I don't.
No, no, it's correct.
The
It's
reason
correct.
is that it was having double one. That's why I chose it.
Yes, actually, that is correct. So for nucleophilic substitution, our system should be more electrophilic in nature. So when you look into this, so when Cl gets removed, So we are getting a system which is more electrophilic. So it is directly bonded to a doubly bonded carbon atom. So doubly bonded is acidic in nature. So it will for example, the doubly bonded is acidic in nature, so it won't go into the resonance. And in this, it is not electrophilic. Like it is not electrophilic because here methyl group is donating its electron to this. Here, the Cl and doubly bonded carbon atom is been separated by a CH2. So it is also electrophilic in nature. And this is very much this is very much reactive because it is a tertiary carbon atom. So correct answer for this is option number 1. Okay.
Wow.
Second,
Ma'am?
huh?
I'm not clear the answer. The first one.
Okay, one second. I'll show you. Okay. Now let us see. So the correct option is first one. Why? Because when I look into the structure, it is CH2 double bond CHCl. Okay. So the chlorine is showing which kind of effect? It is showing a positive mesomeric effect. Why? Because we can say chlorine has lone pair of electron, right? So it will go under resonance and this bond will shift over this bond. Sorry. So this bond will break and it will come over carbon. So what will get? CH2 minus CH double bond Cl plus. So this is showing plus M effect, that is positive mesomeric effect. So due to the partial double bond character between C and Cl, that is vinyl chloride, so we can say there is partial double bond. Now between carbon and chlorine there is partial double bond. Like it is not a permanent double bond. The permanent double bond is between this carbon and this carbon. So there is only a partial double bond. Why? Because there is presence of lone pair of electron. So lone pair is busy with resonance. So we are getting a hybrid structure. Again, this negative part will come over here and this will get stabilized. Okay. So there is a partial double bond between carbon and chlorine. That's why vinyl chloride is least reactive towards nucleophilic substitution. Why? Because chlorine
Also,
is, hello, huh? Pardon?
what about the second thing? The second there is also second thing for a double bond, right?
The
Two
third
options.
one.
Ah, yeah, third one.
Talking about third one, yes. Why? Because when I draw this third structure, it becomes CH2 double bond CH2 Cl. Now chlorine is also having a double bond. If I'm shifting double bond or lone pair over here, is there any double bond? No. There is not any alternate double single bond. But
Yes.
here, if I'm for resonance, you need an alternate double bond system, alternate single double bond system. Okay. Now they're talking about least reactive. In the first structure, the chlorine ka lone pair is completely busy in resonance. So it won't react with any other incoming nucleophile, right? So that's why it is least reactive in nature. So basically, the when any halogen is directly bonded to a doubly bonded system, then that is known as vinyl. And always remember, These vinyls are always, they are least reactive towards nucleophilic SN reaction, nucleophilic substitution reaction. Why? Because the lone pair on carbon chlorine is, it is busy in resonance, so it won't react with the incoming nucleophile. So for the
Then
nucleophile, huh?
what
Pardon?
about what about electrophile? The same thing, vinylic carbon.
Yeah, yeah, that would be, yes. If it is least reactive in nucleophilic substitution, so it will be more reactive in electrophilic substitution, vice versa.
Okay, ma'am.
Okay. So the one thing is that they have positive, just have to keep in mind that they have positive mesomeric effect. Okay, done. Done. Okay. Uh, this is the second question is ozone in stratosphere is depleted by, yes, very good. One second. Okay, this is the application part. Actually, we haven't done that, right? Yeah, we didn't do that. Okay. Yeah, yeah, we haven't done the application part. Okay. So just within 5 minutes we'll complete the application. There are just 2 4 compounds which we have to keep in mind, and then we'll again solve these questions. Okay. I just forgot about the application only. Okay. So basically there are one, two, three, four, and five and six compounds which we have to keep in mind. So the first compound which is coming under application, that is dichloromethane, which is known as DCM, dichloromethane, which is very important organic reagent which is used in laboratory synthesis. That is DCM, dichloromethane. Okay. So basically it is used as a solvent, and it is used in paint remover, it is used in aerosols. Basically they are used in aeroplanes. So you just have to keep one thing in mind, they are widely used as solvents. For any extraction process they use a DCM. Basically dichloromethane is a very it is, what do you think, dichloromethane, is it miscible or immiscible with water? Mm-hmm. No, with the name, just no methane. No, it has chlorine with it. So actually, it is immiscible. If you put in one test tube with water and DCM, so there will be formation of two layers. And always remember, always, whenever there is chlorine in any compound, it would be more denser than water. So it will present at at lower part, and the in upper part there will be water. And apart from chlorine, if there is any other sort of compound, so it would be less denser than water. But all chlorinating agents will be more denser than water. Just have to keep this mind because we have been taught like this. Okay. So basically, what are the harmful effects? So it basically harms the central nervous system. So whenever we are working with DCM, we have to take proper precautions by wearing mask and stuff like that. Because if it's not like at only one exposure you're getting, your central nervous system has been. It's not like only for in first exposure your central nervous system is getting affected. No, by continuous exposure your central nervous system will get affected. Okay. And okay. So basically, like obviously This is a very basic thing. Whenever we are working with any sort of chemicals, you have to take proper precautions, like wearing gloves, wearing masks, wearing clothes which are actually fit with it. Actually, it is not loose, like your sleeves are just fluid. No, you just have to wear things which are appropriate. So these are the basic things which you have to keep in mind. So dichloromethane, the thing is that you have to keep the structure in mind, which is dichloromethane. So it is, methane means one carbon, dichloro means there is presence of two chlorine group. Now just fulfill. So dichloromethane, so it is CH2Cl2. Now, okay. Next is trichloromethane, that is sorry, trichloromethane, which is chloroform. I know everyone knows about chloroform, right? The structure is CHCl3. Basically, it is nothing but what? Chloroform. Yeah, it is used to make people unconscious. But it's not like that. We have, like, I have worked with chloroform, but I have never was in that mode of unconsciousness. It's like if you're getting direct, if you're directly smelling it, you'll find you'll have that dizziness, but you won't get unconscious. That is strong chloroform. So this is one of the most common thing. Chloroform, they are used for making people unconscious. Okay. Then what are
You
the?
didn't
It is not on. Huh?
you didn't smell it.
I did, but we used to have proper precautions. Like if you are opening the bottle, you don't have to open it in front of your nose, because if you're opening the bottle, the gases, that time the gases are very heavier in nature, so it
Ah,
would directly make a person dizzy. Like he won't become unconscious, but he will feel like, okay, chakkar aa rahi hai, kind of.
ah,
Okay.
ah.
So it is not only it is not only to make people unconscious, it also has positive outcomes. So
What?
basically, in every organic preparation, the chloroform is used. Again, this chloroform is highly denser than water. So it
Hmm?
is used in the preparation of insecticides, pesticides, and stuffs like that.
Hmm?
Okay. Then comes this prions. Okay. We'll just write the structures of prion.
Now, what is the answer? Answer
Huh?
is three. Answer is three for question number two.
Question number two, answer is
Me too.
no. It is actually, sorry, a second. The answer is one.
How?
Pardon?
How the answer is one?
Okay, we'll just get into this application in the coming next lecture, because the next lecture is going to start now. Will
Okay.
it be fine?
So you're saying tomorrow you will start this thing?
Uh-huh.
Okay.
Inshallah, I think. Okay.
Tomorrow you're going to take the class, right? Or sir?
Yeah. Okay. I'll come or sir will come.
Okay.
But we'll complete this chapter.
Okay.
Okay, okay. Uh, After this, you'll have physics lecture.
Yes.
Okay then. Sure. Thank you so much.